Let's consider another example. Example 14. If the profit of producing X number of items is given by P, where P equal to X cube minus 2700X, then how many items need to be produced to maximize profit? So here we have profit expressed as a function of X, X being the number of items, and we want to determine how many items that we need to produce in order to maximize profit. So we start with differentiating P with respect to X. So dP dx equal to derivative of x cubed is 3x squared. Derivative of 2700x is just 2700. Now if you let we let dP dx equal to 0 to maximize the profit. So we obtain 3x squared minus 2700 equal to 0. Now we can then rewrite that equation as 3x squared equals 2700. Hence x squared is equal to 900, and this results in a value of plus or minus 30. So x minus 30 and x equal to plus 30 are stationary points. So to determine the nature of stationary points, minus 30 and plus 30, so we put the value of x under the horizontal line, dP dx above the horizontal line. At minus 30 dP dx is 0, at plus 30 dP dx is 0. So the number of items produced cannot be a negative value, so we know x can't take this negative value in this question. So we just need to verify that x equal to 30 maximizes the profit. So we need to determine if x equal to 30 maximizes P. So if you substitute a number slightly less than 30 into the expression of dP dx, we'll obtain a positive value for dP dx. And if you substitute a slightly a value for x slightly greater than 30 and evaluate this expression, we will get a negative value for dP dx. So this shows that in fact x equal to 30 maximizes P, hence the number of items that will maximize profit is x equal to 30. Now let's look at another example, example 15. A rectangular block has a square base with each side having dimension x. The height of the rectangular block is y. If the volume of the block is 1 meter cube, what should be the dimensions x and y that will minimize the surface area of the block? So let's draw the shape of the box. So the dimensions of the base area is x, and x it's a square base, and the height of the block is y. So we can clearly see there are two sides, the top and the bottom. This is the top and the base, which has area x squared. So area is in the top is x squared and the bottom base is x squared. So the area of those two sides is 2x squared, and on the side we have the area is xy and there are 4 sides, so the surface area on the sides is 4xy. So we've written the surface area A in terms of the given dimensions x and y. We've been given an additional piece of information. We've been told that the volume is 1 meter cube, so we need to use that information. So we know the volume is 1 and volume is given by the base area, which is x squared times the height of the block, so y. So we can then express y in terms of x, so y can be written as 1 on x squared. What we are interested here is to minimize the base area, so A is 2x squared plus 4xy. We've got this additional equation. The expression for base area has 2 variables. We have this additional equation, so we can substitute for y in the expression for A to get A in terms of 1 variable only. So if we substitute for y, y is 1 on x squared. So if we write that, so now we have A in terms of 1 variable, 2x squared plus 4 on x. So here we are interested in minimizing A, so we will find dA dx, minimizing A with respect to the dimensions of the box. So if we find dA dx, we have 4x as the derivative of 2x squared, minus 4x raised to the power minus 2 is the derivative of 4 on x. So if you let dA dx equal to 0 now, then we obtain 4x minus 4 on x squared equal to 0. So this equation implies that 4x must equal 4 on x squared. So 4's can cancel, which results in x cubed equal to 1. Hence x equal to 1 is a stationary point. So we need to now verify if x equal to 1 is in fact a minimum. We need to verify if x equal to 1 minimizes A. But before that, when x equal to 1, we know according to this equation that y also has to be 1. So x equal to 1 and y equal to 1 are the dimensions. So we need to verify that x equal to 1 in fact minimizes A. So let's put x below the horizontal line, dA dx above. So dA dx is 0 when x is equal to 1. Now if you substitute a value slightly less than 1 in the expression for dA dx, this expression, if you substitute a value slightly less than 1, we will obtain a negative answer. And if you substitute a value slightly more than 1 in the expression for dA dx and evaluate the right hand side, we will get a positive answer. So in fact, x equal to 1 minimizes A. So the dimensions that minimizes the surface area is x equal to 1 and y equal to 1.